In this video, we'll be breaking down the passage crude mixture analysis and purification. First, we'll start with a passage analysis, what I would pay attention to, what I notice, and then we'll move on to breaking down the questions. So first, we have a research group that is investigating the synthesis of an asymmetric ester through nucleophilic substitution. So I would probably highlight asymmetric ester, that's our product, and the mechanism by which it occurs is nucleophilic substitution. The reaction was conducted by combining compound A with compound B in DMSO at 25 degrees for 4 hours in the presence of potassium carbonate. So I might just highlight those extra molecules that were present in case they ask about them. But of course, we have figure 1 and figure 2, which show us compound A and compound B. One thing I noticed particularly in figure 2 is that they tell us that this is the nucleophilic reagent. So we know that this is the nucleophile, which is going to tell us a little bit more information maybe about how that substitution reaction occurs. Compound A possesses a single stereocenter and was obtained as a single enantiomer. So given the fact that it's obtained as a single enantiomer, tells us, that this reaction is stereospecific and, doesn't come out as a racemic mixture. One reactant was also added in stoichiometric excess, so unreacted starting material would remain in the crude mixture. The reaction vessel was maintained under anhydrous conditions throughout the procedure. So shows things about, what is potentially the excess reagent is something they could ask about. And of course, anything to do with enantiomers, racemic mixtures, pretty high yield. So I would pay attention to that. But I would say generally, right, this second paragraph tells us a little bit more details about how the reaction occurred. So if I need more details, I'll go back there. Following the reaction, an aliquot of the crude mixture was diluted with ethyl acetate and analyzed by thin layer chromatography, which they could definitely ask us about, using a 3,1 hexane ethyl acetate mobile phase. So when I see that, I think about that mobile phase looks pretty nonpolar to me. So this is probably normal phase TLC, not reverse phase TLC, with a nonpolar mobile phase and a polar stationary phase. And we got 3 distinct spots on a developed plate, and our RF values are in this table. Then further, to isolate the product, the reaction mixture was diluted with diethyl ether and washed with sodium bicarbonate solution, 5% weight per volume. So I'd probably just highlight that. The organic layer was collected, dried over anhydrous magnesium sulfate, and concentrated under reduced pressure. Further purification was achieved through fractional distillation under reduced pressure. So highlight that because they could definitely ask us about distillation. Next, the purified product was obtained in 78% yield. Polarimetry measurements indicated that the product was optically active with a specific rotation of -34. So that tells me that we did get most likely like a single enantiomer out of it, which we kind of talked about previously, and that's its specific rotation. NMR confirmed the expected conductivity, and the molecular ion peak and mass spec matched the predicted molecular weight. So, that basically just tells us that we confirmed that this is the product we expected through those 2 different techniques, which they could potentially ask about. So to me, these last few paragraphs are some more basically experimental techniques that if they ask us about further, we could definitely return to those paragraphs. So moving on to question 1, they're asking about the aqueous sodium bicarbonate wash is intended to remove the excess reactant from the organic layer. Which component is removed? So the first thing I notice is they say excess reactant. So when we say excess reactant, there's a few things that I think in this list that are not reactants at all. So I'd probably rule those out. The product and the DMSO are not really reactants in this reaction. So I would be between compound A and compound B. Next, I would identify that sodium bicarbonate, that is a base, right? So if this is a base, bases tend to react with acids, right? And if I kind of revisit this, what I see is that we washed it with a sodium bicarbonate. The organic layer was collected and dried over anhydrous magnesium and concentrated under reduced pressure. So to me, it seems like from that sentence, it tells me that the product is intended to end up in the organic layer because that's what we collect and dry and purify. And we want this reagent to end up in the aqueous layer, right? So if this base reacts with an acid, when I look at my two things, this is what I immediately recognize as the acid. And if I react that with bicarb, then I'm going to get a deprotonation reaction, which is going to make it more soluble and end up in the aqueous. So the answer here would be compound B, because that is our acid that is going to react with that base, enter the aqueous phase, and then leave just the product in the organic layer. So next here, we've got question 2. Based on the reaction conditions described, which mechanism most likely operates in this transformation? So kind of my first question is it SN1 or SN2? I could try to figure that out on my own, or I could read the explanations and see what, speaks to me a little bit. However, one thing that I think may point me a little bit towards one of these is I think about, well, which is my electrophile and which is my nucleophile? And I want to kind of evaluate those and see what I think, right? So they told us that the second one was a nucleophile. And generally, a carboxylic acid is not a very good nucleophile. So I would call this a pretty weak nucleophile generally. But it is negatively charged, right? Especially at pH 7. So, it has the potential to, be a nucleophile in an SN1 or an SN2 reaction. And then what I notice is this is a 2' alkyl halide, which kind of sits in the middle of SN1 and SN2. It could go either way. So I don't get a lot of information, in my opinion, from just the molecules that are being reacted. I think it could go either way just based solely on the structures. So visiting our answer choices, what I would say is because the secondary substrate forms a stabilized carbocation intermediate. So I would say that's true about SN1 reaction, but is it SN1, right? Keeping going, with SN2, because the reaction uses a polar aprotic solvent and an anionic nucleophile, I would say that both of those things are true, right? It's polar aprotic and it's an anionic nucleophile. The carboxylic acid would definitely be anionic. So that's true as well. SN1, because DMSO stabilizes the leaving group through hydrogen bonding. So with DMSO being a polar aprotic solvent, it is going to have a partial negative charge on that sulfoxide group. So the leaving group would leave as a negative. So it doesn't really have the hydrogens because it is aprotic that would stabilize the leaving group through hydrogen bonding. So to me, I can rule that answer out because there would not be hydrogen bonding with the leaving group, which would be Br minus with a polar aprotic solvent. With D, SN2, because carboxylic acids are strong nucleophiles in protic solvents. So I would probably rule that one out as well because, it's not a protic solvent. And so then I'm left between A and B. So from my interpretation of this passage, one thing that I notice is that we get a optically active product at the end, right? So I point that out, especially in the context of this, where it says compound A, one of our reactants, was also stereospecific, right? It was present as one enantiomer. And so to me, that lends itself more towards SN2 rather than SN1, because SN1 would form a racemic mixture of the products if that was the mechanism. And because our final product was optically active, it can't be a racemic mixture. Racemic mixtures should come out to a specific rotation of 0 because they are racemic. So that is how I would probably end up deciding between SN1 and SN2. But that one's pretty tricky because I feel like with the molecules themselves, I don't know that I would be able to pick it out. But I think that those two things together help me figure out that there was inversion of stereochemistry or still have a single enantiomer. And so therefore it would have to be SN2. With question 3, so if the concentration of compound A is doubled while keeping all other conditions constant, what effect would this have on the initial reaction rate? So compound A, right, is our electrophile in this reaction. And this kind of requires the knowledge that we have from question 2, right? Is this SN1 or is this SN2? Technically, in either reaction, doubling the amount of the electrophile, in both cases, it's first order with respect to that reagent in either SN1 or SN2. So our answer choice B here is correct because we are first order with respect to that substrate. So overall, an SN2 reaction would be second order, but it's first order with respect to the nucleophile and first order with respect to the electrophile. So that is why the answer is B and not C. So it's tempting because when you think SN2, you probably think second order, which is true overall, but not in respect to that substrate. And then ruling out A, right? This would be true for, well, I guess it just isn't true at all. Should be only electrophile concentration affects SN1. That would be a true statement. So not A. And then the rate would decrease because excess substrate inhibits nucleophilic attack. Probably not. So that gets me to B. Right, moving on, we've got an IUPAC nomenclature for compound A. So the first thing I would do is, find my longest carbon chain. That's going to help me rule out some things. And I get 1, 2, 3, 4 carbons, which is going to be butane. So I would probably rule out B immediately because propyl would be incorrect. That's not the longest carbon chain that's possible. And then the next question is, which way do I number it, right? Do I put one here or one there? And our rule is that we need our highest priority substituent, which is in this case bromine, to be the lowest possible number, which means we have to order a number from 1 to 4 like that, which would rule out answer choice D. From there, I still have to decide whether I think this is R or S. So then I would do my priorities. So bromine would be first priority. This would be second priority because those are, a tie. They're both carbons. However, this one is attached to another carbon, whereas this carbon's only attached to hydrogens. So that's why that would be second priority. And then that would be third. So if that is my order, and then understanding that my hydrogen is in the back already, then this is my direction of my circle, which leads me to R. Great. All right. Next, we have question 5. If the ester product was obtained as a racemic mixture, which approach could be used to resolve the enantiomers? So I'm looking for something that's going to specifically interact with one enantiomer over another. So A is an achiral silica gel column chromatography. So if it's achiral, that's not going to help. B, chromatography on a chiral stationary plate. I like that, right? Because something chiral can interact with a specific enantiomer or something else. Fractional distillation will separate based on boiling point, which is a physical property, not a chemical property. And when we're separating enantiomers, anything with the physical properties will not help because those would be identical with both of the enantiomers. And for D, extraction with aqueous sodium bicarbonate. Again, this would react the same with either, right? This has nothing to do with the stereospecificity, and so we would have to go with B. Question 6. So assuming the reaction proceeds with an inversion of configuration at the stereocenter, right, which we do believe that it does because it is SN2. What is the absolute configuration of the carbon bearing the oxygen substituent in the product? So here, the first thing I would think about is, well, what was my reagent? My reagent was R, as we determined in question 4. So after inversion of stereochemistry, which we know occurs in SN2, the product should be S, right? So I can basically rule out A and C, but I just want to make sure that the explanations are correct, right? So in B, because backside attack inverts the spatial arrangement of substituents, that is true. S, because the product has a negative specific rotation. So it is true based on the passage. However, just because something has a negative specific rotation does not mean that it is S. And positive specific rotation does not mean that the product is R. So that's kind of a misattribution there. And so our answer then has to be B. Right. And I guess, with A, it would attack from the opposite face as the leaving group. So that doesn't make sense. And then this has nothing to do with priority rules. All right, question 7 here is asking us about the TLC analysis, which reveals 3 different spots with 3 different RF values. Based on the passage information, which compounds are represented by these spots? So I would probably go back to this paragraph and read about the TLC. So the TLC talks about how An aliquot of the crude mixture was diluted with ethyl acetate and analyzed by TLC. So keyword there is the crude mixture. So this is unpurified. So it should have all of the reactants and reagents in addition to the product in it because it has yet to be purified. And also, we know we didn't have a perfect yield of this reaction. So it did not go to full completion. Therefore, we can infer that we would have both compound A, compound B, and our product all present in the crude mixture prior to purification. So that leads us to pick answer choice A. However, the reason I would rule the other ones out, I don't think DMSO would show up. That's the solvent, right? That shouldn't show up as a spot. I don't think it's possible to have an elimination byproduct. We don't end up with a hydroxyl group, in our ester, right? Normally elimination, we would need to have like an OH group hanging off to be eliminated. And then D, two diastereomeric products, an unreacted compound A. I think, first of all, our product is optically active, so I would assume we don't have, a racemic mixture, but I don't think we would get diastereomers either. If anything, we'd get enantiomers, but even that's not the case because our product is optically active. There's not really a possibility to be diastereomers with respect to the product. So that's how I would pick answer choice A.